Good morning, it's May 21st, 2018. I'd like to go deep into history today, digging up an old thread from physics forums from 2011. I'd like to go deep. I'm going to investigate whether this person, Anamitra, um, whether he had a good point and whether he was basically trolled to death or if he was kicked off physics forums by the moderator trolls. So Anamitra says length of the line element does not change in transformations, subjecting to the conditions of continuity, differentiability, one-to-one correspondence, etc. ds squared is invariant with respect to transformations, subject to the conditions. Difficulty here, there are many types of transformations, and I think this has to be broken down case by case to talk about what transformation explicitly you're talking about. But he says, let us have a look at the following transformation, the projection transformation. That seems like a reasonable transformation to do. The projection transformation, as I understand it, is, okay, here's your eye over here, and you're looking over here at objects, buildings, trees, and then you're taking those buildings and trees and mapping them either onto, like that corner gets mapped onto there, either onto a kind of a sphere around you or onto maybe a plane surface in front of you. So you could do either of those as a projection transformation. But mainly it's taking a 3D environment and mapping it onto a two-dimensional space. Now his description is you are standing under a hemispherical roof, so all I would need to do is convert this into, or basically turn it 90 degrees counterclockwise. So here is our roof. The floor is a flat surface. A curve is drawn on the ceiling. We take its projection onto the floor. So we're going to we draw a curve on the surface of the roof. Let's give this a little bit more of a three-dimensional quality to it, and imagine the roof coming around. Something like that maybe, and we'll draw a picture on the roof, which is going to be like a la la la, and it'll be projected down onto the floor, a la la la. So then he says the line element for a hemispherical ceiling is r squared d theta squared plus sine squared theta d phi squared. So this defines a couple of things, that the angle from the roof, I think, is theta. The angle coming this way is phi. So he's going to have the actual length of this path element be calculated, just a tiny path element. R is the radius of the thing. And so I'll just draw a couple of lines in there to indicate that there's an R. D theta is how far we move away from this center point up here. D phi squared is the distance that we move kind of along this direction. So d phi would be different depending on where you are on your theta. So that's why there's a sine theta in there. Is that the same ds squared? Yeah, because sine theta so sine theta is proportional to the radius of this circle. So if sine theta, or if theta is 90 degrees, sine theta is 1, and you use the whole hemisphere. When sine theta is 0, this is not going to have any contribution at all, changing phi. Or yeah, when theta is 0, then sine theta is also 0. So you wouldn't have any contribution to going around the circle at all. The transformation for the projection, because he is transmove, he's basically projecting that S straight down onto the plane of the floor, and x equals r sine theta cosine phi, y equals r sine theta sine phi, and that is correct. And then he says, for an infinitesimal projection, we get from the geometrical conditions that ds prime squared is equal to dx squared plus dy squared. So so we're looking at I've drawn an S down here, so that wasn't really intentional, but so the so the ds prime here refers to the length of the projected shadow shape on the floor, and the ds refers to the path length of the shape on the curved roof. So Anamitra, he says ds and ds prime are not identical, and then he repeats ds and ds prime are not identical. I guess that's a good repetition. So in general relativity, we must consider only such transformations that leave ds unchanged. For an arbitrary, well-behaved transformation, the length of the line element may change. Okay, he did not say ds and ds prime are not identical twice. That was a problem when I was copying it over to my other software. I ended up copying that line twice. All right, but in general relativity, we must consider only such transformations that leave ds unchanged. I'm not sure. I don't think I necessarily agree with that premise. But I do agree that we should use transformations that use, well, that if we're looking at a situation like this, we should leave the dx, the dy, and the dz unchanged. If we're trying to find the length of this s, don't map it to a plane. If this is the s we're talking about, we should leave it in that plane. So that is the answer to Anamitra's question. That we should not, in general relativity, I don't know if it's a must, but projection is fine. But if we're going to talk about this curve in the surface, we should remain in that surface. We shouldn't project down onto a plane. For an arbitrary well-behaved transformation, the length of the line element may change. Okay, so anyway, I think I would agree with this statement if we said we must consider only transformations that leave dx, dy, and dz unchanged. For an arbitrary well-behaved transformation, though, the length of the line element may change. So in particular, Schwarzschild, well, what is the line element? Is the length of the line element going to be dx squared plus this is the length of the line element? Yeah. This is the length of the line element. And in the case of this one, this is the length of a projection of the line element. ds prime is a length of a projection of the line element. If you had the full thing in here, as a matter of fact, this is, you would need to put in dz as well. And you would find that dx squared plus dy squared plus dz squared would be, and this is the Jacobian times the Jacobian transpose, would come out to be dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. And when you do this, then these actually come out equal. But when you cross off this and this, then these are not equal. And that becomes the projection that Anamitra was talking about. Okay, what is PAllen's first response? Your construction is simply wrong. Given a coordinate transform, you have to derive the transform metric. You don't just assume it. What you've done amounts to saying, if I stretch and flatten a hemisphere to a plane, I've changed the geometry. Surprise. Well, no, his construction wasn't wrong, and his transformed metric was not incorrect. He had the correct metric, and if he stretches and he didn't stretch it or flatten a hemisphere to a plane, he just projected it. So, and that changed the geometry. And P. Allen said, um, based on the, yes, I can label points on the hemisphere using the floor, but since I want to preserve geometry, I derive a non-Euclidean metric for the floor coordinates that accomplishes this. Why would you do that? Why? What? And he says, you simply assumed a Euclidean metric and gotten nonsense. No, he assumed a Euclidean metric and actually, I mean, he didn't get nonsense. He got something right. I mean, it's either right or wrong. R sine theta cosine phi, R sine theta sine phi. Those look like what you do in spherical coordinates. That's the general simplest form. It's not nonsense. And anyway, to get the real metric, you can compute the Jacobian and do a matrix multiply. Sure, and that's something that I suggested. So to get the real metric, you can compute the Jacobian, do matrix multiply. That's what the real metric is right there, the Jacobian times the Jacobian transpose. Or you can manipulate differentials, leading to a valid relationship between the dx, dy, and d theta, d phi. Sure. And he's assuming that we consider r a constant in your construction. This is a 2D coordinate transform on a 2 surface. 2D coordinate transformation. It's not though. It's a 2D. It's a 2D coordinate transform from one surface to another surface. That's what it is. As I think he got it right. You're not. And then phi equals inverse tangent of y over x. That's not wrong. It's or is it y over x? Theta equals inverse sine square root of x squared. Yeah, I've been using arctangent. I've been using arc cosine on both of these. Arc cosine theta equals arc cosine of z over square root of x squared plus y squared plus, is it plus z squared? No, that would be, I think plus z squared. And phi is, okay, yeah, so this is opposite over adjacent. opposite over adjacent. So that's correct. Square root of x squared of this would be opposite, and this is opposite over hypotenuse. So yeah, looks like this is correct determination of phi and theta, but why? Um, okay, take d of these, plug in to the theta phi line element. Take d of these, then you get the correct x comma y line element to preserve geometry. And no, you don't, because you get the same answer either way, whether you use the x, y, and z or the r theta phi, or this form, or the form that he gave, which is a little easier, x equals r cosine theta phi sine cosine theta sine theta cosine phi, and y equals r sine theta sine phi. And this, he's giving variables that aren't even available for use. Square root of x squared plus y squared plus z squared right there. You can't even do this derivative if you leave r equal 1 in there, because you're in the wrong format if you do that. So that's good. There's an actual mistake here. So if there's a mistake, then I can say, okay, maybe because I have a lot of respect for PAllen. Generally, he's he's on top of things, but so I like to see some error in his work rather than just him making no mistakes, but expressing it in another way that just confuses people. So it's good to see that he has that r in there, and then he specifies we consider r a constant in your construction. So since he has that, you can see that he's going to make a mistake there if he tries to do the Jacobians with that 1 in there, or with that constant value of r in there, when the Jacobian is a function of x, y, and z, and he doesn't have square root of x squared plus y squared plus z squared in there, it's going to give him a problem. Okay, then Wannabe Newton comes along and says, I don't even know how you determine the metric components after the coordinate transformation. You don't have theta and phi explicitly in terms of the new coordinate, so how did you evaluate g a alpha beta this times g alpha beta? So I'm going to go into something much more recent, something George Dishmen sent me just the other day, which was this article from Wheeler, and this was from October 28th, 2010. So it was just a little bit before that post from Anamitra. And we've got this g sub I j r squared sine theta. And here's our ds squared. Let's zoom into that, and we'll just compare that. We'll just compare that to Anamitra's equation. We got ds squared equals r squared times d theta squared, r squared d theta squared, plus r squared sine squared theta d phi squared, plus r squared sine squared theta d phi squared. So these are the exact same equation that is used in Wheeler's text. So what he's showing here, what Anamitra is showing here, is that this is an equation for a projection of the surface of a sphere onto the surface of a plane. What Wheeler is saying is that this ds squared actually represents the 3D. What is he saying? What he's saying is that r equals constant is moving this into a, he's saying r equals constant gives this, uh, what am I saying? Anamitra recognizes that this thing is the line element for a surface of a sphere. Now looking at Wannabe Newton, I just realized I don't know who Wannabe Newton is talking to. So the third post, he says, I don't even get how you determine the metric components after coordinate transformations. So who is he talking to? Is he talking to Anamitra, who has that r squared and r squared sine theta squared into his diagram? Or is he talking to PAllen, who has put you who's given theta and phi? He doesn't have theta and phi explicitly in terms of the new coordinates. But okay, but I would say it's like just exactly the opposite. Um, theta and phi, theta and phi are given in terms of x, y, and z. X, y, and z are given in terms of theta and phi. That's how it works. But he's saying you can give theta and phi explicitly in terms of the new coordinates. Um, but yeah, what is this? Anamitra had the theta and phi and r implicitly in terms of the x and y coordinates. PAllen mixed them, and so he has an r in here, which may or may not be an error. I'll have to look over it. Probably, I'd be surprised if it was really an error. But anyway, he's expressing a lot of consternation, saying your construction is simply wrong. I don't think his construction is wrong. What I think is wrong is right here. In general relativity, we must consider only such transformations that leave dx, dy, dz unchanged. ds can change. It changes in, for instance, the Schwarzschild metric. But we must consider such transformations that don't project down from a spherical surface, or yeah, from a spherical plane surface to a Minkowski to a flat plane. All right.